Hello, friend. Welcome again. In this video, we're going to continue our discussion about convolutional deep neural networks and applying them to vision tasks and image processing tasks. So in this video, we're going to concentrate on using what are known as pre-trained models. So using a pre-trained model can be a highly effective approach, especially if you only have like a small data set, but you want to get good performance, like good image classification performance on it. So a pre-trained model is a model that was previously trained on a large data set. So typically we're going to look at this one where we're going to use something called the VGG16 architecture that was trained on the ImageNet computation data set that I've mentioned before. So this data set has like 1.4 million labeled images, and the task was it was a multi-class classification where there was 1,000 different output, 1,000 different labels that we were trying to predict from that data. So the idea is that, remember that convolutional networks learn a hierarchy of increasingly more higher level visual features. So we can often reuse that hierarchy successfully and apply it to different tasks. So we don't have to relearn kind of the basic edge detections and slightly bigger components. We can reuse those. Okay, so let's look how we do that. So let's start with talking about the feature extraction. So using the feature extraction of a pre-trained model. So, so feature extraction consists of using the representations that were learned by a previously trained model to extract interesting features from new samples. Okay, so remember, so convolutional networks are like a stack of convolutions and max pooling layers traditionally, right? So if we take a trained neural network, you can divide that into two parts. The series of the pooling and convolution layers. So that's the thing that really learns this feature hierarchy. So this part here, right? And then on top, there's usually one or two dense layers, which is the classifier that's trained to use those representations for the particular task. So like for ImageNet to do an image classification on the 1,000 label multi-class classification task, okay? So if we want to reuse a pre-trained model, usually we're going to just throw away that classifier for the specific task and reuse some or all of the convolutional base. Okay, so then that consists of, so we need to use this convolutional base, but we need to add in, our own dense layer or two and train it. Okay, so we can be reusing the features from the pre-trained model that happened on the convolution layers, but train it on a different classification or some other kind of task. Right? So let's see how we do that using Keras. So Keras has quite a few pre-trained models available for you to make doing things like this relatively simple. So we'll use the VGG16, which was a model I mentioned before that had some success. So it was one of the big ones that was doing early successes on the ImageNet model. So there's more sophisticated ones now available, but this makes a good example. So if you want to use a model, you can look in the Keras applications, and there's various ones like VGG16. There's other ones in there, exception models and other things. So this is like doing a load model. We're just doing a load model from Keras, but for a pre-trained model that's available. So these three parameters specify we want to use a checkpoint that was from this model that was trained on ImageNet. We're not going to include the top. So we've actually already only included the convolutional layers. We threw away the final dense layers that were doing the actual prediction or classification at the end. Now, this ImageNet data wasn't 180 by 180, so some things had to be done in order to make it possible so that we could reuse these. So we are saying, okay, what is going to be our actual input shape that we need to reuse this pre-trained model. Okay? So let's look at the layers that this model had by doing a summary. So if you look at this model architecture, it should look pretty much the same as what we were just doing. So one big difference is that instead of one convolution layer, there's two convolution layers followed by a max pooling. Another, it is deeper, so there's actually 5 blocks of these. So notice they named these. But these 5 blocks are essentially repetition. So there's each block has 2 convolutions followed by a max pooling layer. They did use padding, so you'll notice that the output from the convolution stays the same as the input, right? So it doesn't modify that. But the max pooling is using a 2 by 2, so it downsamples by 2. So they go from 180 to 90 to 45 to 22 and so on. So, but we repeat the pattern we talked about before. So the size of the feature maps goes down, but the number of features, so they start off at 64, 128, and then they double in size up to the last 2 blocks. They didn't double the last one. I don't remember why. So they had 2 final blocks that just used 512 feature maps, but they did reduce the size, 45 down to 22 down to 11. So the final max pooling that comes out of this is only 5 by 5 with 512 of these features that were learned in this hierarchy. And notice since we already removed the top here, that's the end here. So in the original model, there was like 2 or 3 dense layers that this was fed into to do the final classification for this VGG network. So at this point, there's 2 ways that we could proceed. And in this example, we'll show both of these. So the first way is computationally faster, but it limits us, so we can't really do data augmentation with this or some other things. So the idea is we'll just run the base that we have over our data set, and we'll just record its output. So we just transform our inputs that we have into outputs, and just keep those as a, we could put these back to files on disk, but this data is so small, we could just output those into a NumPy array. And then we'll just train a new network, which would just be a dense layer or 2, using these NumPy arrays as input. So this is fast and cheap because it's only required running this convolutional base once for each input image, but it won't allow us to use data augmentation. But then we'll also look at extending the model. So we could just take this model, tack on before it, tack on our data augmentation, after the input layer, but before we're going here, and then add on some dense layers and just do a full training, right? So that will allow us to have the data augmentation that we want. So that would be slower, computation more expensive, but we can do data augmentation. So let's look at the first approach first here. So first do feature extraction without data augmentation. So we'll start by extracting the features without data augmentation, which is relatively straightforward. So we've got our TensorFlow data sets, the same as we used in the previous video here. So this function here, all it does is, it uses a loop to read out the data from the data set in batches. And then notice here, we do have to do some pre-processing. We'll talk about that in a bit here. So we have to actually pre-process the image, which is what the VGG16 expects, that this pre-processing happens to all images that are fed into it. But then, we just use the convolutional base that we loaded before and use the predict. So the output of that will be the predictions, the output will actually be the output from the last max pooling layer that we have here. So the output will be in this shape for each of the samples, right? So we're pulling these out in batches size of 32. That's how we define these TensorFlow data sets that we had. And then we're actually just keeping these all on a list, and at the end we call np concatenate, so it returns it actually as a NumPy array. So we have a NumPy array of all of the prediction outputs for the input images and all of the labels for the input images. So that shouldn't take too long to run, but there are 5,000 images each in each of our data sets, test, training, and validation, less than the validation. So the extracted features that we just did should be of shape samples. So we have our sample dimensions, but 5 by 5 by 512. So you see why, right? So for the training, there was actually only 2,000 images in our training data set. So now after we do this, the training features that we got back is actually a NumPy array of shape 5, 5, 12 with 2,000 samples in it. Okay? And again, you should be able to predict that from looking back at the base, this VGG16 base that we're using. That was the output shape from the final max pooling layer that we had. Okay? So at this point, we can do training again. We've got this data set, so it's already actually been fed through the convolutional layers. So these represent the highest level features that were output by VGG16, running them through the 5 layers of convolutions that it had, right? So all we need to do for training is we just need a network with a final dense layer, okay? So actually, yeah, I forgot. So we do something a little bit more complex. So we do 2 dense layers with some dropout. So we are going to have to fight overfitting here. But we're going to take, we're just going to have inputs of that shape, 5, 5, 5, 12. So we're going to be reading in like these train features as input to this network that we're going to train. Our task is still the cat versus dog task. So at the end here, we need our usual dense layer with a single output that's using sigmoid activation so we can do binary classification. And we'll use binary cross entropy as our loss function. Okay? So let's see what we get with that. So notice, we've got a really small network here because we're relying on the pre-trained high-level representation that comes out of VGG16 in order to do a lot of the heavy lifting for us. Okay, so let's train a model for 20 epochs and see what performance that we get. So that training should go real quick because everything's really small now. It's just a NumPy array in memory, and we've got a relatively small network. So if we look at our learning curves as usual, so notice that so loss does go down to 0, so maybe we're overfitting, but train validation seems to level out. But in particular, so notice the level that we're getting for the validation accuracy. Right? So remember, it was about around 80% for the best model. Well, we probably could have done a little bit better, maybe 85%. But now, using the pre-trained base, we blow that away. We get 97%, maybe 98%. So yeah, if we load the best model that we saw by validation loss, we should typically get above 97%. Okay, I didn't quite get that. So around 96%, not around 97%. But that's still much better, at least 10 percentage points better than what we saw before. So we reach a validation accuracy usually around 97%. This is due to the power of reusing those high-level feature maps learned by the VGG16 base of convolutional layers. It was trained on much, much more data than we're using here, millions of images. Yeah, we're potentially overfitting relatively quickly. So validation loss rises, maybe levels out, but it rises right away. So we never see it kind of going down. So if we could use data augmentation, we might even be able to improve on this performance, and some other methods for fighting overfitting here. So let's do that. So if we want to use data augmentation to fight that potential overfitting that we're having, we want to use the second technique. So this is slower and computationally more expensive, but it will allow us to use data augmentation and some other things. Okay? And we can probably improve even a little bit more on what we just got. Okay? So to do this, we're just going to create a model where we chain on our inputs and our data augmentation onto the convolutional base, and then add in pretty much the same dense classifier that we just did on the output. So one important thing on this, though, is that we have to first freeze the convolutional base. We don't want those weights to be changing. We don't want those to be trainable anymore. Okay, because if we did, the things that it learned would very quickly just be wiped away, right? So by freezing these, conceptually, they're not trainable parameters anymore. They're just weights that go through a layer that don't get updated. Okay. So let's reload it again and chop off the top of the VGG16. And we'll just set everything on all the trainable weights on these to be false, right? So we can just do that for the whole model by just setting the trainable parameter to false in the Keras API here. Okay? So we can set it back to true. So before we do that, there were 26, is that right? So there were some weights that were trainable on the base if we set that to true, but we don't want anything to actually be changing when we do our training here, right? So if we set that to false, everything is 0 here. I can't remember, that doesn't seem quite right, but that might be the number of trainable layers in the whole model. I think that's the number of weight tensors is why it's 26. So there's like 26 layers that have sets of trainable weights on there. Okay. So so now we can create our model. So we need to have our data augmentation stage put on front, our frozen convolutional base in the middle, and then our same kind of set of dense layers, and we'll keep like a dropout on the bottom, right? So it looks something like this. So we have the data augmentation that we saw before. So we'll have our inputs that we need, 180 by 180 by 3 color channels with the augmentation. We do need to do that VGG16 pre-processing. So whatever these images are, VGG16 base won't work unless we pre-process this input. So that's often needed because there was pre-processing done for, and that's what the VGG16 base expects. Then we have the frozen convolutional base, and then we have our dense layer and dropout dense layers that we're going to be actually training. So this is pretty much all this going to be actually be trained again. So these will be the only weights that are modified of things down here. Okay, so let's see what that how that works. So we'll train this model over 50 epochs. But with the same kind of setup as we did before. Okay, so once training is finished there, this will take a lot longer than the previous one, not only because, you know, we're doing a few more epochs of training, but, you know, it's got the convolutional base in between there, so it takes longer to train. But let's look at the learning curve history right away. So notice it doesn't look like it's overfitting anymore. Our performance will usually be a modest gain over what we saw on the previous model here using the data augmentation. So usually above 98% or right around that. Sometimes it won't look like it did too much more, but it's probably a little bit of an improvement. And the improvement is probably significant, you know, so once you get up to the top, you know, half a percentage point consistently better represents a significant improvement over previous things. So yeah, I mean, usually I'll get 97, maybe 98% around there, 97.5. So another final quick thing, when we're reusing a pre-trained model like this, we can actually fine tune it. So if I go back to our figure about feature extraction with a pre-trained model, so remember that the trained convolutional base represents a hierarchy of features, so a feature hierarchy, but you know, the features at the lower level are more general, right? So the features down here are going to be things like edge detectors and things like that, but as you go up, the feature maps at the top of the hierarchy can be kind of specific to the ImageNet task, right? So there might be things on here that are representing like the 1,000 classes, trying to identify those in the images. So it can be useful to unfreeze like maybe 1 or 2 of these top layers and retrain those to try and get high-level features that are more specific, to learn high-level features that are more specific to the task that you want to work on. Okay? So that's what we're going to be doing in this last example here. So you do have to be careful here. So the caveat is that it's only possible to fine-tune some of the top layers of the original convolutional base once the classifier on top has already been trained. So if the classifier isn't already trained, the error signal propagation will just destroy the updates will be too big. It'll just destroy any layers that you unfreeze. It'll destroy their representations. So the actual steps you have to do if you want to do this kind of fine tuning is, add our custom dense layers on top of the already trained base and our data augmentation on the front, so on the bottom. Freeze the network base, do the training. So, we already did those 3 steps before, right? So we actually want to start from the network that we just trained. So now we already have a trained network. It would be safe to unfreeze some of the layers and continue training for a bit more epochs to see if we can get any further improvement by fine-tuning 1 or 2 of the convolutions at the top of our previous model. Okay. So yeah, we already completed those steps 1 through 3. So we're going to unfreeze the block 4. So we're going to keep frozen all the things up to block 4 and only unfreeze the block 5. So there was 2 convolutions, or I guess there's 3 convolutions in block 5 that we're going to unfreeze and allow those weights to change and learn our specific task. And so as a reminder, I should have done this. So up through block 4, we're going to freeze. On block 5, there was actually 3 convolution layers. So all these had 3 convolution layers followed by a max pooling layer. So we're going to allow those to try and learn our high-level representations for the cat versus dog. So here, there's no easy way to do that. So if we set everything to be true, but then we go through and iterate and reset all of the first 4 blocks to be false. So here, the -4, we know that the last 4 layers are the ones in block 5. So we're basically everything that's before these last 4 layers, we set back to false here, effectively freezing blocks 1 through 4 and leaving block 5 layers trainable. Okay. So we can just use our label that we had loaded, our model that we had loaded before, the best one that we had seen, and start it training from that point with these layers unfrozen. So we can actually also be updating these 3 convolutional layer representations. Okay, so let's do that for another 30 epochs. And another thing, so I should mention that he did actually reduce the learning rate in this example as well. So apparently it was still kind of too big. It was destroying. So it's just another thing to keep in mind. So this fine tuning might not always work. You have to be careful that you don't destroy what you already have in the base layers. So this just further makes it so that we're only taking really small steps in this fine tuning. So let's go ahead and let that fit for 30 epochs. So once that's done, as usual, let's jump right to looking at the accuracy on the test data set. So usually when you do this with the fine tuning, you should consistently get 98%, maybe a little bit higher. Okay, so usually you will see that improvement. So yeah, we just breached 98% on this model, which was the best one by validation loss that we saw on this training run here. Okay, so in the original Kaggle competition, this would have been a top result, but it's not quite a fair comparison because they didn't have access to pre-trained networks like this. But we're getting this result on training with only a small subsample of the original data, so that the original competition used the full 20,000 or 25,000 samples or whatever there were, right? But I guess kind of a big takeaway on that is that the difference between training our own model from scratch versus kind of the big effects you can get from using a pre-trained base to do that. So if you only have a small data set, it is worth trying to see if you can use some pre-trained model bases on your data set to get a good improvement. Okay, so with that, so just a couple of things real quickly to remember about what we talked about here for the pre-trained models. So pre-trained models on large imaging data sets are available through the Keras API, so it makes it convenient if you're using Keras. There's a lot more than the VGG model that you can look at. VGG is actually relatively old, so there's even some newer ones. We'll see the exception coming up in future lectures here. So the convolutional layers of such pre-trained models, they've learned a powerful hierarchy of features from low-level edge detections and things like that up to more abstract concepts at the higher levels. And it can be useful to leverage those features that are represented by such models, especially if you need to build some sort of image processing on a relatively small data set. You don't have a lot of data to train with. So there's two basic approaches to using pre-trained models. So you can just extract the features first and save those into a NumPy array or save those to a hard drive and then train with the extracted features. Or you can actually kind of train from end to end, but make certain that you freeze the weights when you do that. And then you can tack on like your data augmentation on top, and then tack on your new dense layers that you want to that you want to learn for your particular task on the bottom. It can also sometimes help to do a little bit of fine tuning. So once you've got a model that's trained, you might want to unfreeze maybe the top layer or two of convolutional weights and see if allowing them to modify their highest level concepts helps you on your task. Okay, so that's it for this video. I hope you stick with me. Stay tuned for our next videos where we're going to get into even more high-level concepts of using convolutional networks for different sorts of image processing tasks. So not only image classification, but like doing segmentation and other things.